Welcome back to the deep dive. We have something very different on the table today.
It feels different, for sure.
Usually when we talk about speed in the tech world, we are talking about convenience.
Yeah.
We're talking about, how fast your page loads, how quickly you can download a movie.
Right. Or maybe low latency in a video game so you don't lag out. Speed is a luxury.
Speed is a luxury.
Yeah.
Exactly. But today, we are talking about speed as a prerequisite for existence. We're looking at survival speed.
Yeah.
The kind of speed that happens not in the blink of an eye, because frankly that is painfully slow for what we're discussing today, but in the microscopic gaps between the blinks.
It's a fascinating pivot, and a humbling one, really. We're so used to thinking in seconds. In the Olympic 100-meter dash, 100th of a second is the difference between gold and nothing.
Sure.
In high-frequency trading, maybe you are worried about milliseconds. But the source material we're unpacking today, it pushes us into the realm of microseconds. It forces us to look at a world where human reaction time isn't just slow.
It's obsolete.
It's obsolete. That's the word the document uses.
That is a heavy word. And the document we are pulling this from isn't a sci-fi novel. It's not some theoretical paper from a university. It is a technical architecture outline. The title is Kinetic AI, the Neurokinetic Bridge.
And it's authored by Gerard King.
And looking at the metadata on this file, this is not for the general public, is it?
No, absolutely not. The intended audience is listed right there, specifically as Tier 0 engineers and sovereign defense architects.
Tier 0, what does that signify?
It means the people who build the absolute root-level foundations of, in this case, national defense systems. Tier 0 usually implies access to the bare metal. You're at the very bottom of the tech stack, where the hardware meets the code.
So the people laying the bricks.
The people who make the atoms that the bricks are made of. And just to underscore the weight of this, the intellectual property value, the FVP listed for this specific outline, is estimated at over $300,000.
So $315,000 to be exact.
Right.
So just to be clear for everyone listening, this is effectively a $300,000 instruction manual on how to take the human being out of the driver's seat of defense systems.
That is the blunt way to put it, yes. But the nuance is really important here. The mission of this deep dive is to understand why that shift is happening, and more importantly, how you actually build a system like that.
Right.
We are looking at the transition from human in the loop, which, has been the standard ethical safety net for decades, to fully autonomous defense. And we aren't just talking about autonomy in the sense that a drone flies itself.
Right.
We are talking about an autonomy that processes strategic thought and executes physical violence within a time frame that completely, utterly defies biological limits.
It's a little unsettling, to be honest. But the goal here is to strip the fear away and just look at the engineering, because the engineering is fascinating.
It's brilliant.
We have a roadmap for this discussion. We're going to start with what the document calls the human bottleneck. Basically, the hard numbers on why we are the problem. Then we will break down the neurokinetic bridge, which is the actual brain of this machine.
The core logic.
Then we'll look at the offensive capabilities, things like seeing without looking and swarm immunity. And finally, and I think this is the most important part, we're going to spend a significant amount of time on security.
We have to.
Because if you build a God machine that moves this fast, you better be damn sure it doesn't get hacked.
And that security section is actually the densest part of the document. It involves concepts like post-quantum cryptography and, something called ethical axioms in silicon, which is a concept I think will stick with you for a long time.
Ethical axioms in silicon.
It fundamentally changes how we think about trust.
Okay, let's not get ahead of ourselves.
Yeah.
Let's start with the problem. The document opens with a pretty ruthless takedown of human biology. It introduces the concept of biological latency.
It does. And it doesn't pull any punches. It puts a hard number on our cognitive ceiling. The document cites a 200 meters plus delay in human neurotransmission.
200 milliseconds.
200 milliseconds. Now, if you spill hot coffee on your hand, it feels instant when you pull away, right?
Right. Instantaneous.
But neurologically, it isn't. That signal had to travel from your skin up your spine, get processed in the brain, and then a command has to be sent all the way back to the muscle. That loop takes physical time.
And that time is 200 milliseconds. In the grand scheme of things, that sounds pretty fast. Why is that considered a failure state in this document?
Because of what's on the other side of the battlefield. The source contrasts our 200 millisecond delay against a requirement of 10 microseconds.
10 microseconds.
10 millionths of a second. The disparity is, I mean, it's almost impossible to grasp. We are talking orders and orders of magnitude here.
It's a different reality.
It is. If you have an incoming threat, the source calls them post-quantum kinetic threats, like a hypervelocity projectile or a drone swarm operating on its own AI logic. It is moving, adjusting, and reacting at microsecond speeds. A human defense system reacting at millisecond speeds is, for all intents and purposes, standing still.
It's like trying to catch a fly with a movement that takes a week to execute.
That's a perfect analogy, and this is what effectively kills the OD loop, isn't it? I mean, in military strategy, the OD loop observe, orient, decide, act, that has been the Bible since the Korean War.
It is the Bible.
Yeah.
Or it was. The theory, developed by Colonel John Boyd, was brilliant for its time. Whoever cycles through that loop faster wins the fight. You see the enemy, you figure out what they're doing, you decide your move, and you do it.
Simple. And if you do that faster than the other guy, you win.
Exactly. But this source argues that the manual OD loop is dead. It refers to human-in-the-loop systems as, what was the term? Legacy vulnerabilities.
Legacy vulnerability.
That stings a bit. It sounds like we were Windows 95 trying to run a modern game.
From an engineering standpoint, in this specific kinetic context, we are. If you insert a human into that loop, you are hard-coding a 200 millisecond latency. You cannot train that away.
No amount of coffee helps.
You cannot caffeine that away. It is the physical speed of chemical synapses jumping across gaps. In a kinetic engagement where the opponent is autonomous, that latency is fatal. The human cannot observe or decide fast enough.
So by the time the neurotransmitters fire in your brain to tell your finger to push a button,
the event is already over. The missile has hit. The drone has passed. The fight is done.
So the premise is, we have to take the human out of the immediate reaction loop, not because we want to necessarily, but because we physically have to if we want to survive in this new environment.
We need a system that mimics a nervous system but operates at the speed of electricity, not biology.
Exactly. And that brings us to the core architecture described in Gerard King's outline, the neurokinetic bridge.
This is the how.
This is the how. The document outlines a two-system architecture.
Yeah.
And it uses an analogy I think a lot of people might recognize from Psychology System 1 and System 2.
Right. Daniel Kahneman's Thinking Fast and Slow. It's a fantastic comparison. In the human brain, System 2 is your logical, calculating, slow mind.
The chess player.
The chess player. It's the voice in your head doing long division or planning a vacation. System 1 is your gut, your reflex, your fast mind. It's what happens when you swerve your car to avoid a deer before you even consciously realize you saw a deer.
That's a great way to put it.
And this document applies that exact framework to machine architecture.
So walk us through the machine version. What is System 2 in this kinetic AI context?
In this model, System 2 is the strategist. This is your large language model, your LLM.
Right.
This is the part of the AI that has read the manuals, it understands the Geneva Convention, it knows the geopolitical context.
This is the brainy part.
It is. It handles high-level mission parameters and, critically, ethical boundary setting.
So it understands context. It knows the difference between a tank and a school bus.
Yeah.
And it knows why that difference matters.
Ideally, yes. It identifies the broader strategic goals. But, just like our own logical brain, LLMs are computationally heavy. They're relatively slow. They need massive GPUs. They take time to generate tokens, which are like words or thoughts. You cannot have an LLM deciding when to dodge a bullet.
Because by the time it generates the token dodge, you are dead.
Yeah.
It's too much processing overhead.
Precisely. You don't want a philosopher deciding when to duck.
You want a reflex.
You want a reflex, and that is where System 1 comes in. The source identifies this as neuromorphic computing. Its role is direct weight-to-motor mapping.
Weight-to-motor mapping. Okay, that sounds incredibly technical. Can we break that down?
Of course. Think of it as digital muscle memory. In any neural network, weights are just the numerical strength of the connections between the artificial neurons. This system maps the input signal, the data from the sensors, directly to the motor output. It doesn't ponder the meaning of the threat. It perceives a specific pattern of pixels or sensor data, and immediately, instantly, triggers a physical response. It bypasses all that higher-level cognitive processing entirely.
But here is where the document gets really, really technical, and I want to make sure we get this right. It talks about bypassing the kernel.
Yes, this is the key.
Now, even for tech-savvy people, the kernel is usually something you just you don't mess with. It's the heart of the operating system. Why is this necessary?
This is the absolute key to hitting that 10 microsecond target. In a normal computer, like the laptop you are using right now, you have an operating system, the kernel, Windows, Linux, Mac OS.
Sure.
When a piece of software wants to move a piece of hardware, say a fan or a drive, it has to ask the OS. The OS then checks permissions, it schedules the task, it talks to a driver, the driver talks to the bus, and finally, eventually, the hardware moves.
That sounds like government bureaucracy.
It's digital bureaucracy. And it is essential for general-purpose computing, but every single one of those steps introduces latency, milliseconds of it. Bare metal AI, which is what this source proposes, eliminates the middleman.
All of them.
It says there is no operating system in the reflexive loop. The neural activations modulate the PWM, that's pulse width modulation, the signal that controls a motor's speed directly on the FPGA fabric.
Okay, let's pause on FPGA. That stands for Field Programmable Gate Array. How is that different from a normal CPU, like an Intel or an Apple chip?
It's fundamentally different. A CPU is a chip that is hardwired to do general tasks, and it runs software instructions one after another very quickly. An FPGA is a chip where you can physically rewire the circuits using code.
Rewire them.
So imagine a chip where the circuitry itself reconfigures to become the algorithm. In this architecture, the AI code isn't running on top of an OS, which is running on a CPU. The AI effectively becomes the electrical pathway that drives the motor.
So it is code talking directly to electricity. There is no translation layer.
Correct. The latency is reduced to the physical limits of the electrons moving through the silicon, and that is how they bridge the gap. The System 2 LLM sets the policy, defend this perimeter, and the System 1 FPGA executes that policy with bare metal reflexes that happen faster than human thought.
That is unbelievably efficient. And honestly, it makes the machine feel less like a tool and more like an organism. It has a thinking brain and it has a spinal cord, a nervous system.
It is a convergence of software and hardware that mimics biology but strips away all the biological inefficiencies. It creates a seamless, instantaneous flow from threat detection to kinetic action.
So we have the brain, the neurokinetic bridge. Now let's talk about the eyes, the offensive capabilities. The source mentions zero latency vision and specifically event-based vision sensors, or DVS.
This is one of the coolest technologies in the robotic space right now. It is a perfect example of biomimicry. Standard cameras, the ones in our phones, on our laptops, are actually incredibly inefficient for this kind of work.
Oh, so they seem pretty good to me.
They're good at making pretty pictures for human eyes, but think about how they work. A video camera captures a frame, a full picture, 30 or 60 times a second. Even if you're filming a brick wall and absolutely nothing is moving.
It's still taking 60 pictures of a brick wall every second.
Exactly. That camera is recording and processing millions of pixels over and over, saying wall, 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 wall. The document calls this frame buffer overhead. It represents a massive amount of useless data clogging up the processor.
It is looking at the whole world all the time instead of just what matters.
Precisely. DVS sensors, dynamic vision sensors, work like the human retina. They don't record frames. They only report changes in light intensity at the pixel level.
What does that mean?
It means if a pixel sees the same thing as it did a microsecond ago, it sends zero data. It stays completely silent. It sleeps. But the instant a pixel changes because something moved across its field of view, it fires a signal, an event.
So it is motion triggered at the pixel level.
Yes. This creates a data stream that is incredibly sparse, but incredibly fast. There is no frame buffer to build or wait for. As soon as movement happens, the system knows. The source calls this seeing without looking.
I like that.
It isn't constructing a pretty image for a human to watch on a screen. It is detecting pure motion dynamics for the machine to react to.
And once it sees something, it doesn't just shoot it where it is. The source talks about predictive interception.
This connects back to the AI capabilities. The system uses multimodal transformers to forecast ballistic trajectories. And the key phrase here, and this is critical, is that it calculates these trajectories before sensors achieve 100% lock.
So it sounds like it's guessing. Is that safe?
It's not guessing, it's projecting. It is, in a very real sense, shooting at the future. It calculates where the target will be in the next few microseconds based on its current vector, its velocity, its predicted acceleration. If you are trying to intercept a hypersonic missile or a maneuvering drone, you cannot chase it. You have to meet it there. It's that old Wayne Gretzky quote, right? Skate to where the puck is going to be, but at Mach 5.
And it isn't just one machine doing this. The outline mentions a swarm immune system.
This takes the concept of the individual ODA loop and scales it across a collective. We are talking about distributed sensor actuator nodes, all connected via 6G ultra-low latency slices.
Swarm immune system is a very specific choice of words. It sounds like biology again.
It is. Think of your body's immune system. White blood cells don't necessarily need to call the brain to ask permission to attack a virus. They signal each other locally, chemically.
They just know.
They just know. In this architecture, if one drone in the swarm sees a threat via its DVS sensor, the entire swarm shares that awareness instantly. The document says it achieves collective synchronization.
So you can't sneak up on just one. If you trigger one, you trigger the whole organism.
Precisely. And because of 6G slicing, which is technology that allows you to allocate dedicated, guaranteed bandwidth for this specific task, that communication happens almost as fast as the internal processing within a single unit.
Okay, so we have a system that thinks faster than us, sees faster than us, using these retina-like sensors. It predicts the future, and it acts as a collective swarm.
That's the architecture.
That is formidable. But it also raises the massive, obvious question, what if it goes wrong? What if someone hacks it? The more digital and connected something is, the more hackable it usually is.
And that brings us to the adversarial vector section of the document. And it highlights a really, really nasty possibility called kinetic feedback hijacking.
Just the name sounds bad. What is it?
Well, imagine an enemy who knows how your sensors work. They aren't trying to guess your password or break your encryption in the traditional sense. They are attacking the physics of your sensors.
Wow.
They could inject adversarial temporal noise, think of it like a very specific calculated pattern of flashing lights or radar pulses, into that high-speed sensor stream.
So like trying to induce a seizure in the machine?
It's worse. The source says this could force the actuator, the motor moving the weapon or the flight surface, into a harmonic resonance failure.
Harmonic resonance, like the bridge that starts shaking in the wind.
Exactly like that. The noise tricks the motor into vibrating at its natural resonant frequency, causing it to shake itself apart physically. It's like breaking a wine glass with a perfectly pitched opera note, but applied to a multi-million-dollar piece of military hardware.
That is wild. You aren't hacking the code, you're hacking the physics of the machine itself.
Or, even worse than that, you could induce a friendly fire loop. If you can manipulate the sensor data just right, you might be able to fool the predictive trajectory algorithms. You could fool the system into predicting a threat where a friendly unit stands.
And because it's acting on reflex.
Because it's acting on that bare metal reflex, not high-level contemplation, it strikes instantly. No time for a double check.
That is the nightmare scenario. Automated friendly fire because of a signal injection. So how does Gerard King propose we stop this? The countermeasure matrix in the source is pretty intense.
It's heavy duty. The first line of defense is lattice-based command integrity, specifically using crystals dilithium signatures.
Okay, I have to stop you there. Aside from sounding like the warp drive in Star Trek, what is crystals dilithium? Is that a real thing?
It is absolutely a real thing. It is a cryptographic algorithm that was selected by NIST, the National Institute of Standards and Technology in the U.S., for the post-quantum era.
What do you mean post-quantum era?
I mean that current encryption, the stuff that protects your bank account right now, RSA and things like that, is based on math that quantum computers will be able to solve very easily, very soon.
They'll just break it.
They'll shatter it. Crystals dilithium is based on a different kind of math called lattice mathematics, problems involving high-dimensional grids that are incredibly difficult to solve, even for a hypothetical, powerful quantum computer.
And they're applying this.
Where?
Where?
Yeah.
To the login screen.
No, that's the thing. They are applying it to every motor command packet.
Wait a minute. Every single time the machine tells a motor to twitch or a flap to move a fraction of a degree, it has to sign that command with post-quantum cryptography.
That is the requirement. It ensures 100% command-to-actuator alignment. If the signal telling the motor to move doesn't have the correct, valid crystals dilithium signature, the motor simply will not move. It ignores the command as noise.
So it completely prevents the hijacking we talked about.
It does. An enemy can inject all the noise they want, but if they can't forge the signature, and they can't because it's post-quantum secure, the actuator is deaf to them.
That is incredibly rigorous. It's like needing a notarized letter for every single breath you take.
It is. But in this environment, paranoia is a survival trait.
There's another layer here too, right? The document calls it temporal watermarking.
Yes. This addresses the timing aspect. It's described as hardware-bound temporal sequencing. So every single movement command is time-stamped at the hardware level. If a command comes in out of sequence, which can happen if an enemy is recording and replaying old signals to confuse a system. That's called a replay attack. The machine rejects it.
So it forces the system to live strictly in the present moment.
Exactly. It has to be the right signature and it has to be the right time. But the most fascinating countermeasure, and the one I really want to dig into, is the third one: ethical axioms in silicon.
This sounds like science fiction.
It does, but this is the game changer. This is the part that I think represents a paradigm shift in AI safety. We talk a lot about AI ethics, right? Making sure ChatGPT doesn't say bad things or an image generator doesn't produce harmful content.
Sure, but those are software rules.
They're always software rules. It's a line of code somewhere that says, if target equals civilian, do not fire.
Right, and software can be rewritten. It can have bugs. It can suffer from prompt injection, where you trick the AI into ignoring its rules.
Exactly. Gerard King is proposing we stop trusting the software for this. He's proposing hard-coding non-combatant and sovereign asset identifiers into the physical logic gates of the FPGA.
Into the physical logic gates. I want to make sure I understand this. The prohibition against shooting a friendly isn't just a line of code. It is a physical barrier baked into the chip's circuitry.
That is the implication. Think of it like a physical keyhole. If the key doesn't fit, the door literally cannot open. It doesn't matter if the AI wants to open it or is tricked into thinking it should. In this case, even if the System 2 AI hallucinates or gets hacked and issues a command to attack a friendly target, the signal would physically fail to pass through the gate on the FPGA because the target's identifier wouldn't match the hard-coded axiom.
The chip itself would just...
It would refuse to execute the kill chain. The electricity would hit a dead end.
That changes the whole conversation about trust. You aren't trusting the software developer or the AI model anymore. You are trusting the chip architect.
You're trusting the physics. It creates an uncorruptible code at the hardware level. It is the ultimate failsafe, the ultimate emergency brake, welded directly to the axle.
And there is one final layer of security mentioned: cryptographic actuation.
Yes. This closes the loop. It provides accountability. Every time the machine actually moves, it must provide a proof of intent hash back to the sovereign node.
Like a receipt.
It's like a blockchain receipt for physical movement. I moved 10 degrees to the left at this exact microsecond, and here is the cryptographic proof that I did it because I was authorized to.
So nothing happens without a verified crypto trail.
Total accountability in a microsecond environment. It makes going rogue mathematically impossible, at least in theory.
Okay, so we have built this high-speed, secure, ethically hard-coded machine. How well does it actually work? The source gives us a scorecard.
It does. It gives us an epistemic certainty score, or ECS, and it's rated at 98.9 out of 100.0.
98.9. That's an A+ in school. That's great. But in a life-or-death situation, my eye immediately goes to that 1.1%. What is that? What's in that gap?
That is the crucial question in any kinetic system, isn't it? 98.9% certainty is incredibly high for an autonomous system operating in a chaotic environment. But that 1.1%, that's the fog of war. It represents the unpredictability of physics. It represents the fact that sometimes the wind blows a certain way, or a sensor gets a splash of mud on it, or a piece of shrapnel blocks the view for a microsecond.
The messiness of the real world.
The things you can't model perfectly.
Speaking of physics, the document lists MBCs, main barrier constraints. What is stopping this thing from being even faster? Why not 1 microsecond? Why not instantaneous?
The laws of the universe, unfortunately. The first constraint listed is literally the speed of light in copper fiber.
You're kidding.
No, you simply cannot push electrons or photons faster than that. We are hitting the physical limits of how fast a signal can travel down a wire on a printed circuit board.
So we are literally waiting on the speed of light. That is a heck of a bottleneck to have. Sorry, physics is too slow for us.
It really puts into perspective how optimized these systems are. The second constraint is thermal throttling of edge FPGAs.
Heat.
Just heat. When you run these reconfigurable chips this fast, processing post-quantum crypto and neuromorphic reflexes 1,000,000 times a second, they generate immense heat. If they get too hot, they either melt or they throttle down, meaning they automatically slow themselves down to survive.
So heat management becomes a tactical constraint.
You can only think as fast as you can cool your thoughts.
And the machine knows this, right? The source also mentions a UVC rating.
Yes, it's listed as UVC-1, which refers to predictive modeling of mechanical actuator wear and tear under extreme G-force.
So it's self-aware about its own physical body.
In a way, yes. This is fascinating because it implies the system is aware of its own physical degradation. It knows that if it pulls a 50G turn to intercept a missile, that maneuver might cause microscopic fractures in its own gears or actuators.
So it has a sense of self-preservation, or at least self-maintenance.
It calculates the physical cost of the movement. It might think, if I make this move, I survive the engagement, but I damage my rotor by 10%. It factors that physical reality into the decision loop. It isn't just a brain in a jar. It is a brain that feels the limits of its own body.
That is a level of sophistication that really bridges the gap between the digital and the physical. It isn't just running code, it is managing a physical existence under stress.
Which is essential for the neurokinetic bridge. You can't have a reflex if you aren't aware of the muscle.
So let's zoom out. We have gone through the tech. We have seen the numbers from 200 milliseconds down to 10 microseconds. We've seen the security crystals to lithium and hardware ethics. We've seen the financial value over 300 grand just for this blueprint. What is the big takeaway here? What does this all mean for the future of defense, for the future of AI?
Well, I think the big takeaway is that we are witnessing the professionalization and the architecting of sovereign AI. This isn't just about making smarter drones anymore. It is about creating a defense infrastructure that is fundamentally inhuman in its capability.
And its limitations,
Right.
or lack thereof.
Exactly. The move to bare metal AI, and especially these ethical axioms in silicon, suggests that the future of defense lies in removing the very things that have defined warfare for all of history: software vulnerabilities and biological delays.
It is a move toward absolute trust in the hardware. We are cementing our rules and our reactions into the silicon itself.
Exactly. It represents a shift where the uncorruptible code isn't a moral stance. It is a technical architecture. It's an attempt to build a shield that cannot hesitate, cannot be tricked, and cannot be bribed because it is physically incapable of it.
And that leads to a final thought I want to leave everyone with today. We talked about ethical axioms in silicon, hard-coding the rule, don't shoot civilians right into the chip. It sounds great. On the surface, it sounds perfectly safe.
It's the ultimate safety feature.
But it forces us to ask a really big question. If we are now hard-coding ethics into the physical gates of a chip to prevent AI hallucinations or software bugs, does that mean we are finally admitting that software on its own can never be fully trusted with these decisions? And if the ethics are in the hardware, who gets to design the chip? Because whoever etches those gates, whoever designs that physical logic, defines the morality of the machine forever.
And that is the ultimate question of sovereignty, isn't it?
Thanks for diving deep with us into the architecture of kinetic AI. It is a fast world out there. Try to keep up. We will see you on the next one.